Hello and welcome back to another episode of Math with Sohn. Today we're going to be going over, for AP Physics 2, the things that you would probably need to know for your magnetism portion of the AP exam. So, the biggest and probably most common thing is that force magnetic is equal to QVB, technically sine theta, and normally for AP, they're going to just make sure that sine is going to be perfectly 90 degrees, and therefore it would be 1, but occasionally you need to use it. Now, this formula is going to be given to you, but you need to know it is when you have a charged particle going through a magnetic field. And that'll be the most typical example. Okay? So, you got charged particle going through magnetic field. If you have crosses, the magnetic field is going into the page. Magnetic field going into the page for crosses. And you would have to use the right-hand rule to determine which way it would go. So in this case, you would have your fingers going into the page, and your thumb would be going to the right. And if it is an electron, you either use your left hand, or you can use your right hand, and then it would be the backhand. So the force magnetic in this case is going to be down, because if you put your fingers, I can't really do it, but if you were to put your hand into the page and put your velocity to the right, you would have your palm facing down. Okay? And it will always be a circular path in the field. Circular path in the field. It is important to know the velocity stays the same. Well, the velocity changes direction. The speed stays the same. Okay, speed stays the same, but velocity stays constant. Now, there's another situation that you can have with a wire. The force magnetic on a wire. Force magnetic on a wire is equal to ILB sine theta. And this is used when you have a wire in a magnetic field. If you have a wire in a magnetic field and you want to find the force magnetic, you have I, the current in the wire, L, the length of the wire. B is not the strength of the magnetic field created by the current, but the strength of the magnetic field in the wire itself. Okay? So, if you were to use the right-hand rule for this, if you use the right-hand rule for this, then you treat the current as the thumb / velocity. Now, I am not talking about the curling right-hand rule. I'm talking about the exact same thing that we had here. So here, we had crosses, we had a velocity to the right. It'd be the exact same setup where you have crosses and velocity to the right, and the force magnetic in this case would be your palm because it's not a negative current. So the force magnetic in this case would be up, and the wire itself would move up, okay? Now, there's a different right-hand rule to determine, see there it is, force magnetic would be up. So there's a different right-hand rule to determine the magnetic field created by the wire. The magnetic field created by the wire will be you put your direction as your thumb, and then you end up curling around. In this case, if we did that, we would have the wire having it come towards us on this side, and then it would end up going away from us on the other side. And the strength of that magnetic field is denoted by B is equal to mu naught I over 2 pi r. Okay? And if you have two wires next to each other, they can interact with each other. If the currents are going in the same direction, then they will end up attracting, and if they're going in the opposite direction, then they will end up repelling. And what we'll need to do to find that actual force magnetic is kind of quite tricky. So you think of one wire by itself, okay? So let's just say we take this left wire. It is creating a magnetic field. This left wire creates a magnetic field denoted by B is equal to mu naught I over 2 pi r. Then the right wire is in that magnetic field. The right wire is in that magnetic field, and if they're in that magnetic field, the right wire would have to use ILB sine theta. But what is the B? The B was created by the other wire. So then if you replace this in for that, then you would end up with an equation that looks like this. I1 times I2 mu naught L over 2 pi r. And it doesn't matter if the currents are the same or different. this would be the formula you use. If the currents are the same, it would end up being I squared. L is the length of wire in the field. But it also could be the length of wire that is creating the field, because the length of wire creating the field would have to be the same amount of the length of wire that is in the field, okay? So, moving right along, we got to deal with magnetic flux. Magnetic flux, in the most basic definition, is how much area is inside of a coil or a circle or some sort of enclosed space of wire loop, okay? And that is denoted by B cosine theta times A, okay? B cosine theta times A. The strength of the field and how much area is enclosed will determine how much flux. So you could either shrink the area or shrink the magnetic field to shrink the magnetic flux. If you ever have a change in magnetic flux, then that will induce a current. There are two versions of how to get that current. Excuse me. Well, if you have a current, you're also going to have a voltage, but they're both on your formula sheet. You got the voltage is equal to the change in flux divided by time. That would equal the voltage, and the voltage would equal BLV. You would use this one anytime you just know the change in flux. You would use this one if you quite literally had a cart going into a field. You would use this length of wire and the velocity that it is moving, okay? So if you have a coil going through on a cart, how quickly is that coil going through the cart would be the field would be the velocity. The length of wire that is on the right side or entering the field would be the length that you care about, not the full length of wire. Only the length of wire that is entering the magnetic field. We do not count these guys right here and here because those are parallel to the field or parallel to the velocity, so to speak. Okay? So, the actual physics behind this is Lenz's law, and I wrote it a little bit wrong. I need to address it. The change in flux will induce a current in the wire, and that will produce a magnetic field that will oppose the change in what is happening to it. So if it is entering a field, it won't want to enter a field, and it'll create a magnetic field in the opposite direction. If it is leaving the magnetic field, then it will create a magnetic field that is the same because it doesn't want to leave, okay? So it's got a love-hate relationship. It's like, I don't like you, and then it loves you, and then it don't leave me. Oh, I hate you, go away, and then it likes you, okay? So the method that I like is the one where there is a car with a velocity, okay? And I always draw it where the velocity is going to the right, where the cart is going to the right. And if you do that, then you look at this portion of the wire only, the part that is entering the field. We would be putting our fingers into the page. The velocity is to the right, and if we do that, our force will be our palm, and we would end up with a force going up. If we have a force going up, that means the current on this side will be going up, and this current will be going, counterclockwise. So in this case, the current will be going counterclockwise. If that happens, and this velocity is only happening on its own, then the cart will slow down, okay? Because there will be a force that will cause it to slow down in the opposite direction. So that is only if it is not having, if it's on its own fruition, okay? So if there's somebody pushing the cart at a constant velocity, it won't slow down, okay? So it will slow down, and it will have a current. If you're fully embedded in the field, there's no change in flux, there's no voltage, there is no slowdown, it's moving at a constant speed. If you're leaving the field, it will slow down again. And we still are going to the right, we would still be having our fingers in the page, the force would still be up, but the force is up on the other side, so now it is going to be going a clockwise current due to the fact that it is going in the other side of the little rectangle, okay? So that's what I drew there. All right. What else? This can be done in a variety of ways. The other ways that it could be done is by reducing the field. If you're reducing the field, that would just be leaving the field. Or if you had a ring fully engulfed and then you turn it to where it's no longer fully engulfed and part of it is engulfed, that would also reduce it. So reducing and adding more can be dealt with in a variety of different ways. You could have a magnetic field where you have a ring over here and you have a wire. If this current goes up, then in this case, you would be in a sea of x's over here. If the current increases, then the change in flux would be going up too. So there's a lot of ways to deal with it. And if that is the case, then you are entering the field, and you're entering the field on this left side over here. So you do have to be careful. Okay. Last but not least, we have the typical mass spectrometer. These are the most famous for the FRQs, but it's not the only version of FRQs that you could have. The other version would be some sort of cart problem where they have a flux or a rail or something like that. So here we have an electron going in. This electron would like to go up to the top plate. It's attracted to that top plate, but it still has a sea of x's that are here that are keeping it, which means that the force magnetic and the force electric must be equal in this portion. Then once it leaves that electric field, then it will be curling in the appropriate direction, and it would curl in a circular path. And they sometimes give you the diameter, but sometimes they give you the radius. The radius of that circular path will be the important part. And it will be QVB is equal to the force magnetic, and the force magnetic is a circular motion, so it will equal mv squared over r. Okay? You need to solve this equation numerous times on some multiple choice to determine if the velocity is more, will the radius be more? If the mass is more, will the radius be more? In my example, I've solved for m. One of the velocities does cancel, but it turns out if the mass is more, the radius is more, which is, to me, counterintuitive, because I would think if the mass is more, it won't be able to turn as much, but that is what it is. The other thing that's very popular is which direction will the electric field be going? Well, in this case, it would have to go down because the electric field is going from positive to negative. So just be aware and be able to problem solve with that. If you know which way the radius is going, you can determine what the charge is going to be. In this case, if we knew the radius was down, if we know the radius is down, you could use your right hand rule to determine, wait a minute, that would be my backhand, and that must mean that this is an electron. If this is an electron, then I would need to be able to figure out like what charge is on the top and what charge is on the bottom, and then which way would the electric field go. So if this was an electron, it needs to go unimpeded. It would want to go up from the electric field to balance out the down from the magnetic field. So just be aware of the problem solving for that. Maybe do a few practice FRQs if you can find them. But until next time, stay positive, and I will see y'all later. Bye.